Assalamualaikum and good day. My name is Siti Nur Sakinah binti Ma'ali. Matric number 2413210555. Today, I will present my project entitled Design, Improvement and Analysis of Office Footrest for the course MMK21103, Computer Aided Engineering, Faculty of Mechanical Engineering and Technology, UNIMED. In this presentation, I will cover the introduction, project objective, scope of project, literature review, methodology, CAD design models, material properties, machine, boundary condition and loading, result, discussion, and conclusion. Introduction. A footrest is commonly used to support human weight and improve ergonomic comfort in office environments. Because it apprehenses repeated static loading, the structure must be strong enough to prevent excessive deformation or failure. In this project, finite element analysis or FEA is used to evaluate stress distribution, deformation, and safety factor. The main aim is to improve the design to achieve a lighter but stronger structure. Project objective. The objectives of this project are: first, to analyze stress, deformation, and safety factor of the original footrest design. Second, to introduce to design modification. Third, to compare the structural performance between design. And finally, to identify the most optimal design in terms of strength and material efficiency. Scope of project. The scope of this project includes 3D CAD modeling, static structural analysis using ANSYS, and comparison of 3 designs. Meanwhile, dynamic and fatigue analysis, thermal analysis, and experimental testing are excluded from this study. Literature review. Previous studies show that rib of grid reinforced structures can increase stiffness while reducing weight. However, a very thin base plate may reduce strength. Therefore, a balanced geometry is needed to achieve good load distribution. This concept is applied in the improved footrest design. Methodology flowchart. This slide shows the overall methodology. The process starts with CAD modeling, followed by importing the geometry into ANSYS. Then, material properties are assigned, machine is generated, boundary condition and load are applied, and finally, results are obtained and compared. CAD design models. 3 designs were developed. The original design is a fully solid plate with 50 mm thickness. Modification 1 used a grid structure with a 3 mm base plate and 12 mm grid height. Modification 2 uses a 5 mm base plate with 10 mm grid height. All designs have the same outer dimension to ensure fair comparison. Material properties. 3 materials were assigned. ABS plastic was used for the footrest base, structural steel for the supporting structure, and rubber for the bottom contact surface. This multi-material setup provides a more realistic simulation. Now, I will continue for part meshing. A tetrahedral mesh was applied to all models. The number of nodes was kept below 200,000 to ensure computational efficiency. Consistent meshing was used for fair comparison between designs. Boundary condition and loading. A fixed support was applied at the bottom of the footrest. A vertical downward force of 700 Newton was applied on the top surface. This represents the load of a human foot during usage. Result parameter. 3 main parameters were evaluated: equivalent of one mean stress, total deformation, and safety factor. Result summary table. Next, this slide shows the result summary table for all 3 designs. For the original design, the maximum 1 meter stress recorded is 22.043 megapascal. The maximum deformation is 1.33 millimeters, and the minimum safety factor is 3.72. This value indicate that the original solid plate design is structurally safe with relatively low stress and moderate deformation. However, it used a higher amount of material. For modification 1, the maximum 1 meter stress increased to 44.249 megapascal. The maximum deformation increased to 2.35 millimeters, and the minimum safety factor decreased to 1.61. This shows that although modification 1 successfully reduced material uses, the thin 3 mm base plate causes higher stress concentration and large bending deformation, resulting in a lower margin of safety. For modification 2, the maximum 1 meter stress is 35.66 megapascal. The maximum deformation is only 0.49 millimeters, and the minimum safety factor is 3.97. This indicates that increasing the base plate thickness to 5 mm significantly improve stiffness, reduce deformation, and provide the highest safety factor among all designs. Therefore, based on this table, modification 2 achieves the best balance between strength, stiffness, and material efficiency. Next, for graph result. This graph presents a clearer comparison of the result. For the first graph, we show maximum 1 meter stress versus design. Modification 1 has the highest stress, followed by modification 2, while the original design have the lowest stress. This confirms that the thin base plate in modification 1 is unable to distribute load effectively. For the second graph, we show maximum deformation versus design. Modification 2 have the lowest deformation at only 0.14 49 millimeters, indicating the highest stiffness. Modification 1 show the highest deformation due to insufficient base thickness. For the third graph, we show safety factor versus design. Modification 2 achieves the highest safety factor, almost 4.0, followed by the original design, while modification 1 have the lowest safety factor. From this graph, it is clearly shown that modification 2 is the safest and most structurally reliable design. I will continue for contour plot. Next, this contour plot shows the stress, deformation and safety factor distribution for each design. In the original design, stress distribution is relatively uniform and deformation is moderate. In modification 1, high stress concentration appear that the center region and large deformation is observed, which explains the lower safety factor. In modification 2, stress is more evenly distributed and deformation is minimal, confirming that the structure is stiffer and better at resisting bending. Now, I will cover for discussion. The original design is strong but use more material. Modification 1 is lighter but produces higher stress and deformation due to the thin base plate. Modification 2 improves stiffness by increasing base thickness, resulting in low deformation and high safety factor. Therefore, modification 2 achieves the best structural performance. Conclusion. In conclusion, this project successfully analyzed and improved the footrest design using CAE. Modification 2 is identified as the optimal design. It produces the lowest deformation and highest safety factor and achieves good material efficiency. Thus, the main objective of this project has been achieved. That is all from me. Thank you for listening.